Hello everyone, and welcome to this video on determining whether a function is one-to-one. Okay, so we've got the word function here. Hopefully you remember what that means. Right? A function is a relation, right? A relationship between two sets in which, every value from the first set, called the domain, right? Every input corresponds or maps to or is related to only one value from the second set, which is sometimes referred to as the range or the set of outputs. So a function, right, every value of the domain corresponds to exactly one value of the range. Okay, now that meant that you could have two values of the domain correspond to the same value in the range, right? There are functions like that. We're going to see in this video today what it means for a function to be one-to-one, right? This is a very specific type of function. In a one-to-one function, not only does every input correspond to exactly one output, but every output is mapped to by only one input. All right, and I'll explain all that. So in this video, I'm going to start off with the definition of a one-to-one function, a pretty basic definition. Then we'll go into a couple examples of maybe a mapping, a function represented by a mapping, a function represented by a set of ordered pairs, and then we'll talk about functions represented by graphs, right? Pictures of functions, and how to determine easily whether those functions are one-to-one as well using something called the horizontal line test. I'll get into that as well. Okay, so on my first page, I define what does it mean for a function to be a one-to-one function. All right. So a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. So that means that if, say, x1 and x2 are different inputs to some function called f, then the value of f at x1 will not be the same as the value of f at x2. Right? So another way to state this, or we could say that each value in the range is mapped to by only one value in the domain. Each value in the range is mapped to or depends on by only one value in the domain. So you're not going to see any repeating outputs. Right? You're not going to see any repeated y values or any repeated values in the domain in the range. Okay. All right, so it's still a function, but one-to-one. All right, so noting this definition, and I'll come back to it. Let's look at some examples. So my first example, I have a function that's just represented by a mapping, little arrow diagram. So in this example and my following examples, I'm simply going to be asked to determine whether the function is one-to-one. Okay, so I have this set of inputs, right? I have a relationship between two sets here: friends, friend names, names of my friends, and birth dates. So you see the arrows are going from the friend names to birth dates. So the inputs, right, the values of the domain are the friends, and the outputs, the values of the range, are these birth dates. Okay. So we have, Max corresponds to November 8th, meaning that, Max's birthday is November 8th. Alicia's birthday is January 20th. Trent's birthday is March 3rd, Wanda's birthday is July 6th, Yolanda's birthday is November 8th, and Elvis's birthday is January 8th. So this is a function, okay? We're going to be looking at things that are functions. All right, this is a function. Because look, every value of the domain only has one arrow coming off of it. Right? Every value of the domain corresponds to exactly one value of the range. So it is a function, right? We're still looking at functions. But by this definition, all right, here, it is not a one-to-one function, and I'll explain why. All right. But it is not a one-to-one function. Okay, so still a function, just not a one-to-one function. Now, why is that? Well, this is because Max and Yolanda both correspond to the same output. Both correspond to, November 8th, that November 8th birthday. All right, so what I'm looking for in a mapping to determine whether or not the function is one-to-one, I'm looking at the output values, right? This output, January 20th, is mapped to by only one input, great. This output is mapped to by only one input, right? Trent, that's great. This output, July 6th, is mapped to only by Wanda, wonderful. This is the problem, right? So I got a function, but not a one-to-one function because of this guy right here, November 8th. There is a value in the range that is mapped to by more than one value in the domain, right? It's mapped to by Max and Yolanda. All right. So if you're looking at a mapping then, and you're asked, well, first off, is it a function? Yes. Every one of the domain has one arrow coming off of it. So it's a function. And if you're asked, is it a one-to-one function, then you're looking at the values in the range. And if there's any value in the range with more than one arrow coming into it, then it's not a one-to-one function. I hope that is clear. All right. Now, if every single one of these values in the range had just one arrow coming into it, then it would be a one-to-one function. But that did not happen here. Okay. So again, remember the definition, right? For any two different inputs, right? Any two different inputs correspond to two different outputs. If it is one-to-one. Well, if it's not one-to-one, here's two different inputs, but they don't correspond to different outputs. So it's not one-to-one. I hope that's really clear. I really want to make sure that's clear. All right, so that was an example where the function was represented as a mapping. Here's another example where I have a function represented as a set of ordered pairs, right? So it's still a function. All right, this is still a function that I'm looking at. All right, because every value, every x coordinate corresponds to only one y coordinate, right? -3 corresponds to 3, and that's it. There's no other x values of -3. -2 corresponds to +2, and that's it. -1 corresponds to +1, that's it. 0 corresponds to 0, and that's it. 1 corresponds to -1, and that's it. You could also make a mapping if you wanted to, right? There's only 5 ordered pairs up here. I could make a picture like in the previous example, where here are my x coordinates, right? The values of the domain. So -3, -2, -1, 0, and 1. And then the values of the range, right? The set of the outputs over here, where those are the y coordinates. Now I'll put them in order. So -1 would be the lowest, and then 0, and then 1, 2, and 3. Still, but these are all the y coordinates, the second coordinates. And then I draw the little arrows, for the relationships that we're seeing. So we're seeing -3 in the domain corresponds to 3 in the range. Right? So -3 to 3. -2 in the domain to 2 in the range. -1 to 1. 0 to 0. And 1 to -1. Okay. Great. So here's a nice arrow diagram. And like I said, it is a function. Right? We can see from here that it's a function. Right? Every single value of the domain has exactly one arrow coming off of it. Every value of the domain corresponds to exactly one value of the range. And it is also, right, and it is a one-to-one function as well. Oops, 1 to 1, sorry, 1 to 1. And it is a one-to-one function. And the reason we can see that is if you look at the outputs. Every single output is mapped to by only one input, right? There are no outputs with two arrows going to them like in the last example. Every output has one arrow coming to it. So this is an example of a one-to-one function. So notice if you didn't want to make the mapping like this, the thing you can look out for if you're given a function written as a set of ordered pairs, if one-to-one, then there's no repeated y coordinates. All right, see, I see a y coordinate of -1. I don't see any other y coordinates of -1. Now, be careful with this because sometimes they might try to trick you and put the same ordered pair twice. Like if I put 0, 0, and then, 0, 0 again in this set, it would still be one-to-one even though there are repeating ones because you have 0 these are the same point, right? So I wouldn't be drawing an extra arrow or anything. It'd be the same arrow again. So there'd still only be one arrow coming into the output of 0. So be careful with this just in case they try to trip you up by throwing in the same ordered pair again. All right, but if I have the same y coordinate twice with different x coordinates, right, that violates the definition of one-to-one, right? Two different inputs should go to two different outputs if it's a one-to-one function. So this is a one-to-one function. Fantastic. Okay, so we've seen examples of functions expressed or represented by mappings, these arrow diagrams, by a set of ordered pairs. Another way to represent functions were with equations and graphs of those equations. So that's what my next couple of examples are on. Now when you're looking at a graph, all right, of a function, now remember you've seen the vertical line test before this, right? The vertical line test was to determine if a graph was the graph of a function, right? If every vertical line hit the graph at most once, then you had a graph of a function, right? Every x value, every domain value corresponded to one range value only, one output. Well, this is just the other way around. I'm looking, are there any repeating y coordinates, right? I'm going to ask, here's the graph of a function. Is this function a one-to-one function, right? Does it satisfy that definition of a one-to-one function? So this time, when you're asked about, do I have a one-to-one function, you're going to be conducting the horizontal line test, which I've described here. So it's just like the vertical line test, right? It's just you're using horizontal lines not to determine if the graph is a function, right? The graph is already a function. You're determining if the graph is representing a one-to-one function, right? A very specific kind of function. So here's the horizontal line test. If every horizontal line, right, that's left, right, if every horizontal line intersects the graph of a function, right, see it's already a function, in at most one point, then that function f is 1 to 1. If there's, this is for every horizontal line. So that means you only need to find one horizontal line that hits the graph more than once. And if that happens, then you don't have a 1 to 1 function. It's not 1 to 1. All right, so let's look at some examples. So I have a graph here. Right? It says I use the graph to determine whether the given function is 1 to 1. So I'm already given the equation for the function here. I know it's a function. Every x will give me one y. Every input will give me one output. F of x equals x to the fourth minus 4x squared. This is a very rough sketch of this graph. The point -2, 0, the point 0, 0, the point +2, 0 would be on it, and it would be going up forever to the left, up forever to the right, and have this kind of wavy looking shape, this W shape almost. Right, a little more, it's not a W exactly. And this should be symmetrical actually. I mean, this is kind of a, I did it by hand. It's not the greatest. Right, but these bumps should be as low as each other. It should be symmetrical about the y-axis. Okay. So the horizontal line test. Now you can eyeball it. Now I have a nice piece of graph paper here, but if you have a straight edge or a ruler, or just use your eyes, here's a horizontal line, just straight left and right, one of these grid lines, right? And I'm using a ruler. The horizontal line test says if every horizontal line hits the graph at most one point, then we have a 1 to 1 function. If you can find a horizontal line that hits it more than once, then it's not 1 to 1. All right, so this horizontal line where my ruler is doesn't hit the graph, so far so good. This doesn't, this doesn't, this doesn't. But then look, as soon as I hit here, this horizontal line, and I'll dot it in, right? That horizontal line hits the graph more than once, here and here. And as you slide the horizontal line up, this horizontal line hits it more than once. It hits it here, 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 and here. This, the x-axis. The x-axis is a horizontal line which hits the graph 3 times. But as soon as you can find one, right? Here's a horizontal line that hits the graph more than once. And again, all you need to do is find one, a horizontal line. So here's a horizontal line that hits the graph more than once, meaning that this function called f, is not 1 to 1. Right? It's a function, sure, passes the vertical line test, but it doesn't pass this horizontal line test. It is not 1 to 1. And again, going back to the definition of what it means to be a 1 to 1 function, right? Every pair of different inputs should give me different outputs. Well, look at this. Here's different inputs, -2 and +2. Those are two different inputs, but they give me the same output, right? They give me an output of 0. So right there, I can see it's not 1 to 1, right? Because I can find a pair of two different inputs that give me the same output. All right, so I've got one more of these. Right, these should be relatively simple. So one last graph here. Here's another graph of, again, it's a function, right? So it passes the vertical line test. Right? If I pass every vertical line will hit this thing only once or 0 times, or at most once. So this is a function, f of x equals x to the 5th plus 4x. Right? So you got 0, 0 on there and a bunch of other points. I just, again, drew a very rough sketch of this. And this is what they call an odd function, right? It has that origin symmetry. You can test that out. And again, I'm just going to say, hey, is this a 1 to 1 function? Well, while looking at the graph here, here's my horizontal lines, my ruler going through the horizontal grid lines, and then this would hit it once, right? Because the graph goes down forever, and the graph goes up forever this way. So this would hit the graph one time, once, once. All right, it looks like no matter where I put the horizontal line, and I'll draw a bunch of these. All right, let me draw some of these in. So here's a horizontal line. Here's another horizontal line. And it really doesn't matter where I go. All right, look at the x-axis is a horizontal line. Here's another one. And I could draw them forever. I could do that till I'm blue in the face. And you see that this horizontal line hits the graph one time. This hits it one time. This hits it one time. This horizontal line hits it one time. So it's looking like what we said, what passing the horizontal line test looks like. It looks as though every horizontal line hits the graph at most once, right? That means once or no times, right? Hits the graph at most once. Leading me to state the following, state the fact that this function f is one-to-one, is a one-to-one function. Right. Great. And remember what the definition was, right? Every pair of different inputs will give you different outputs, right? Here's -1 and +1, give me totally different outputs. -5 and +5, totally different outputs, right? Every pair of different inputs will give me different outputs. That is what it means for a function to be one-to-one. Hopefully that is clear. Now there are algebraic ways that I'm not going to do here in this video of proving that a function is one-to-one using the definition, but I'm not going to get into that in this video. This is more geared toward an intermediate algebra course. So that's all I've got here. Just know the definition, right? A function, right? Something that's already a function is called a one-to-one function if every pair of different inputs will give me different outputs. Okay, if every pair of different inputs gives me different outputs. Great. All right, and as I like to say at the end of these videos, do the best you can. Please try to learn the material on your own before you go looking for help. I have found over the years that people who take the time and the effort to learn something on their own tend to remember that material better and remember it for longer and are more proud of themselves for it, right? Boost confidence in their abilities, which is always a good thing. So obviously read the material, right? Read through the author's examples, perhaps even try to work out the solutions to an author's examples before you see how the author did them, and then compare your work with the author's and see if you can learn from some mistakes there. Obviously work on tons of exercises, practice problems. Practice makes progress. It's the only way to get better at this stuff. And check for solutions to those, if they're made available to you. Just check how you're doing, track your progress, see how you're doing. And don't just give up on a problem after 1 or 2 attempts. Very often in mathematics, there are several approaches that'll work for any particular problem. So if after several approaches to a problem, or problems, if you're still struggling, still having trouble, I would actually suggest to you to go back and read the material again, perhaps even a third time, right? More slowly, more deliberately. Take good notes, and then later organize those notes so they're easier for you to read and understand. Because if you've been working on problems, as you should, you'll get a better idea, you'll have a better understanding as to what the author wants from you in that section, what the author feels is important material about that section, what the author is asking of you. So when you go back and read again, you can more easily point out the important material. And some things might pop out at you as well that didn't the first time you read it. And it'll make working on the problems that much easier, hopefully. Okay, but if after that Right, if after several read-throughs of the material and several attempts and approaches at the problem set, if you're still struggling, still having a hard time, you know, after all that work, all that time and effort trying to help yourself, it is not a sign of weakness whatsoever to go out looking for help. Again, after you've tried it yourself, right? Don't just immediately run to a tutor as a crutch, right? And how can someone help you if you haven't taken the time and the effort to try and help yourself? So ask a teacher, a tutor, a friend, someone in your class who you know knows the material well and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos online, videos like this one, or plenty of ones out there that are better than this one. I assure you they're out there and they're easy to find. But just keep at it, keep practicing, stay persistent, don't give up. And above all, and I think this is the hardest thing for most people, is to stay positive, believe in yourself, believe in your ability to make it through your frustrations and learn this material and be successful. Believe in your abilities, because it's in those times when you're struggling, when you're failing, when you're making mistakes, it's in those moments when you're frustrated that you actually have the opportunity to learn the most and also learn the most deeply. If you can persist and persevere and push through your frustrations and work to the point where you actually know how to fix your mistakes, and you'll remember that material far better and far longer than someone who just got it right the first time and breezed through and never gave it a second thought. Because there was emotion there for you. When emotion's attached to information, it builds memories, long-lasting memories. There was blood, sweat, and tears when you struggled and pushed your way through to learn that material, as opposed to the person who just breezed through. You'll remember it far longer than they will, I promise you. Right. On average. Right. There are some exceptional people out there, sure, but on average, I'd say you'd remember it far longer than someone who just breezed through and didn't give it a second thought. Okay, so please stay at it, keep at it, stay persistent, keep practicing, don't give up, and stay positive, all right? Believe in yourself, because I believe in you, and I know you'll get it if you don't give up. Thank you very much for watching.